This is Srikanth, Assistant Professor of EEE Department. Today, in Elements of Electrical and Electronics Engineering subject, we are discussing the Kirchhoff's laws. In the Kirchhoff's laws, there are two different Kirchhoff's laws. In that, first one is Kirchhoff's voltage law and the second one is Kirchhoff's current law. The Kirchhoff's voltage law states that in any closed loop, the voltage across all the elements is equals to 0. That is, algebraic sum of voltage in a closed path is equals to 0. So here, when we take any voltages, here let us consider some voltage sources are connected in a closed path. Those, if you write the algebraic sum, this is V1, V2, V3, V4. Here, for writing the algebraic sum, we have to take the current direction into consideration. So, if the current enters the negative terminal, negative we are going to consider, that is minus V1, and here also current is entering the negative terminal, so minus V2, and current is entering the positive terminal, plus V3, and current is entering the positive terminal, plus V4, which is equals to 0. And we can also say this as the positive voltages is equals to the negative voltages. Sum of positive voltages is equals to the sum of negative voltages. That is, V1 plus V2 is equals to V3 plus V4. This is the statement of Kirchhoff's voltage law, where Kirchhoff's voltage law states that algebraic sum of voltage in a closed path is equals to 0, or sum of positive voltages is equals to sum of negative voltages. And this is the way we can take for one circuit which is having one voltage source and 3 resistors are connected, R1, R2, R3. And these are the nodes which we are taking, A, B, C, D. And this is the voltage which we are having, VDA, this is the voltage source we are giving. And across the resistor R1, the voltage is taken as between the two nodes, A and B nodes. That node voltage is taken as VAB. And between node B and C is taken as VBC. Between C and D is taken as VCD. If we are going to write the KVL, for writing the KVL for this circuit, we have to give the directions for the voltages, that is sign convention, that is positive and negative. If the current enters the, for any resistor, the voltage drop can be taken as the current entering terminal is taken as positive, current leaving terminal can be taken as negative. Okay, here the current always flows from positive to negative, that is from higher potential to lower potential. So current will start from this direction, from the positive to, that is towards A node, and here the terminal which is entering is, this is the terminal, so this is taken as the positive and this is taken as the negative. And in the same way here also we have to take current entering terminal is taken as positive and leaving terminal is taken as negative. And here also current entering terminal is taken as positive and leaving terminal is taken as positive. leaving terminal is taken as negative. So here, as we have already discussed, the current enters the terminal. Here Kirchhoff's voltage law can be written in different ways. Here now we are taking one way, that is, if the current entering terminal is negative, we are going to consider that voltage as negative. If the current entering terminal is positive, that voltage we are going to take it as positive. So here the current entering terminal is for this source is minus VDA. So here current entering terminal is the negative. Current entering terminal is negative. So that is minus VDA. That is minus VDA. Minus VDA. And here the current entering terminal is positive. So that voltage drop can be taken as positive. That is VAB. That is VAB. And the next one is current entering the positive terminal. So plus VBC. And current entering, here also current is entering the positive terminal. So plus VCD. So here VDA is equals to VAB plus VBC plus VCD. This is the KVL equation. From this equation, we can say that whatever the source voltage should be equals to, the voltage drops across the resistors. Source voltage should be equals to voltage drops across the resistors. This is the way we are going to write the KVL equation for any given circuit. Now, from the Kirchhoff's voltage law, we are going to find the equivalent resistance when resistors are connected in series. Now let us see that how we are going to calculate the equivalent resistance when the number of resistors are connected in series. Now let us take n number of resistors connected in series. So here this is the voltage which we are going to give for the resistors. This is Vs, let us consider, and this is the current which is flowing through it, Is, R1, R2, R3, so on, Rn. And here let us consider one equivalent resistance plus minus Vs R equivalent. Here n number of resistors are connected in series, that is R1, R2, R3, so on, Rn. So the voltages across the resistors are VR1 plus or minus VR2 plus or minus VR3, so on, plus or minus VRN. So from the Kirchhoff's law statement, Kirchhoff's voltage law statement, that is algebraic sum of voltages in a closed path is equals to 0. So in this closed path, Vs is the source and VR1, VR2, VR3, so on, VRN are the voltage drops across the resistors. So here, if we write the KVL in the loop, minus Vs plus VR1, current is entering the positive terminal across the resistors VR1, VR2, VR3, so on, VRN, that is equals to 0. Algebraic sum of voltage in a closed path is equals to 0, where Vs is equals to VR1 plus VR2 plus VR3, so on, VRN. So here, this is the voltage equation for this particular circuit. Now VR1 is equals to here these elements are connected in series. When the resistors or any other elements connected in series, the current will be same in all the elements. Current is same in all the elements because there is no other path for the current to flow. So VR1 is equals to Is into R1 and VR2 is equals to Is into R2. This is from the Ohm's law where V is equals to IR at constant temperature, and VR3 is equals to Is into R3, so on. VRN is equals to Is into Rn. This is the voltage equations across the resistors. Now if we substitute these values into the above equations, Vs is equals to Is into R1 plus Is into R2, Is into R3, so on, Is into Rn. That is equals to Is into R1 plus R2 plus R3, so on, Rn. Let us consider this as equation number 1. So here we are replacing all these resistors with a single equivalent resistance. Single equivalent resistance, that is R equivalent. Now let us write the KVL equation for this. That is Is. So from this, if we write the KVL, that is V R equivalent. So that is current is entering the negative terminal of the source, that is minus Vs plus V into R equivalent, which is equals to 0. So Vs is equals to V R equivalent. Vs is equals to V R equivalent. So from this, Vs is equals to I into R equivalent. This is equation number 2. If we are making these two circuits are equal, then these two equations should be equal. If we compare with equation 1 and 2, that is Vs is equals to Is into R1 plus R2 plus R3, so on, Rn, and here Vs is equals to I into R equivalent. Vs, Is both are same. So from this we can write it as R equivalent is equals to R1 plus R2 plus R3, so on, Rn. This is the equivalent resistance when n number of resistors connected in series. N number of resistors connected in series. So now we got the R equivalent as R1 plus R2 plus R3, so on Rn. Here, if only two resistors are connected, if two resistors are connected, then R equivalent will be equals to R1 plus R2. Now, here if you see this equation, R1 plus R2 plus R3 so on Rn, always the equivalent resistance of any two resistors or n number of resistors when are connected, always the equivalent resistance value will be greater than the all individual values, because this is the addition of the resistors. So always equivalent resistance will be more than the individual resistances. And another note, let us consider, if n equal resistors are connected, connected in series, n equal resistors are connected in series, then R equivalent will be, if let us consider that all the resistors are of equal value of R resistance, R ohms. So R plus, so on R, that is equals to n times the R. So when the equal resistors are connected, the equivalent resistance will be equals to how many resistors are connected in series, that number multiplied with the resistance value. This is corresponding to the equivalent resistance when the resistors are connected in series. Now we will go with the same Kirchhoff's voltage law. We are going to get the voltage division rule also. So now let us discuss the voltage division rule from the Kirchhoff's voltage law. Now we are going with the voltage division rule. When we are going with the voltage division rule, let us consider two resistors are connected in series. Let us consider two resistors are connected in series and which is connected to a voltage source of Vs, that is R1, R2. This is the Is. And here we need to calculate what is the voltage across R1, what is the voltage across R2. And that equation we have to generalized for the voltage division. That is nothing but the voltage division rule. How the voltage is divided in series connected elements. Whereas when we go with series connected elements, the current is same because there is no other path for the current to flow, and voltage will be divided across the resistors corresponding to the resistors. Okay, so for that we have to calculate what is the voltage across each and every element when the elements are connected in series. Okay, here now we have taken from the Ohm's law, VR1 is equals to Is into R1, VR2 is equals to Is into R2. VR1 is equals to Is into R1 and VR2 is equals to Is into R2. Now If we write the KVL in this loop, that is minus Vs plus VR1 plus VR2 is equals to 0. That is equals to Vs is equals to VR1 plus VR2. Here, if we substitute these values, let us consider this is equation number 1, this is equation number 2. If we substitute equation 1 in equation 2, if we substitute equation 1 in equation 2, that is Is into R1 plus R2 will get. That is, from this we can write Is equation as Vs by R1 plus R2. Is equation as Vs by R1 plus R2. So here we got the current equation. Let us consider this as equation number 3. If we substitute equation number 3 in equation number 1, then we will get the voltage across each resistor. Okay, substitute equation 3 in equation 1. Substitute equation 3 in equation 1. That is, VR1 is equals to Vs by R1 plus R2 into R1, and VR2 is equals to Vs by R1 plus R2 into R2. This is the way we are going to get the voltage across the each resistors. Vs into R1 by R1 plus R2 is the voltage across R1 resistance. Vs into R2 by R1 plus R2 is the voltage across R2 resistance. From these equations, we can conclude that voltage across any resistor is equals to the voltage applied across the series connected elements multiplied with that particular resistance, value divided by sum of resistors connected in series. In the same way, here also we got VR2 is equals to Vs into R2 by R1 plus R2. So here the voltage division can be done with voltage division rule is nothing but voltage across any particular series connected element is equals to the total voltage multiplied with that particular element resistance value divided by sum of resistances. This is the voltage division which we are going to get from the Kirchhoff's voltage law. The next one is Kirchhoff's current law. Next law is the Kirchhoff's current law. Kirchhoff's current law states that algebraic sum of currents at a node is equals to 0. Or in other words, we can say that entering currents to the node is equals to sum of entering currents to the node is equals to sum of leaving currents. Sum of entering currents is equals to sum of leaving currents. And here you can see clearly this is the node which we are having. Here there are 5 currents. Some currents are entering and some currents are leaving. Here I1 current is entering towards the node. I2 current is also entering. I3 current is also entering. These 3 currents, I1, I2 and I3 currents are the entering currents, and I4 and I5 currents are the leaving currents. So the currents entering the node equals the currents leaving the node. Currents entering the node equals currents leaving the node. That is I1 plus I2 plus I3. I1 plus I2 plus I3 is equals to I4 plus I5. This is entering currents equals to leaving currents equation. If we consider the algebraic sum as the equation, we have to consider entering currents as the positive and leaving currents as the negative. That is I1 plus I2 plus I3 minus currents, leaving currents are I4 and I5. Leaving currents are I4, leaving currents are I4 and I5. So these currents are taken as negatives minus I4 minus I5. But the resultant will be same. I1 plus I2 plus I3 is equals to I4 plus I5. The resultant current is same, but the representation is different. And from this Kirchhoff's current law, we are going to get the equivalent resistance when the resistors are connected in parallel. When the resistors are connected in parallel. Now let us take the equivalent resistance of resistors when the resistors are connected in parallel. Now equivalent resistance when the resistors are connected in parallel. When the resistors are connected in parallel. So here now n resistors are connected in parallel. Let us consider R1, R2, R3, so on Rn. Here we need to calculate R equivalent. Now for calculating R equivalent, we are going to write the current equation at this particular junction. Because currents, if we give any supply to these resistors, if we give any supply to these parallel connected resistors, that is Vs, the current Is will be flowing in this particular direction, and this current is divided into n types, that is I1, I2, In. So here Is is equals to I1 plus I2, so on In. This is the current equation at this junction node. Let us consider this is node A. Okay, so this is the current Is is equals to I1 plus I2 plus so on In. Here I1 is equals to in parallel elements always voltage will be same. In parallel elements always voltage will be same, current will be divided. So I1 is equals to Vs by R1 and I2 is equals to Vs by R2 and so on. In is equals to Vs by Rn. So from this, if we write Is is equals to, if you substitute these values into the above equation, Vs by R1 plus Vs by R2, so on, Vs by Rn, which is equals to Vs into 1 by R1 plus 1 by R2 plus so on 1 by Rn. This is the Is equation we got. Let us consider this as equation number 1. Now let us replace all these n parallel resistances with a single resistance, single equivalent resistance, that is Vs we are giving, and this is the R equivalent and Is. And from this we can write Is is equals to Vs by R equivalent. This is equation number 2. By comparing equations 1 and 2, by comparing equations 1 and 2, by comparing equations 1 and 2, 1 by R equivalent is equals to 1 by R1 plus 1 by R2, so on 1 by Rn. This is the formula for calculating the equivalent resistance when n resistors are connected in parallel. When n resistors are connected in parallel. Now 1 by R equivalent is equals to 1 by R1 plus 1 by R2, so on 1 by Rn. If, let us take one note, when n equal resistances are connected in parallel, when n equal resistances are connected in parallel, 1 by R equivalent will be equals to 1 by R plus 1 by R, so on 1 by R. That is equals to 1 by R equivalent is equals to n by R. From this, we are going to get R equivalent is equals to R by n. So from this, we can say that R equivalent value is equals to R by n. That is, when n equal resistances are connected in parallel, equivalent resistance will be reduced by n times. And with this, we can say that always equivalent resistance value should be less than the individual elements, when they are connected in parallel. In series, it will be always more than the individual elements, whereas in parallel, it will be less than the individual elements. Now, another note, when note 2, this is note 1, when two resistors are connected in parallel, when two resistors are connected in parallel, R 1 by R equivalent is equals to 1 by R1 plus 1 by R2. Simple we can write this equation with simple with simple notation, that is 1 by R equivalent is equals to R1 plus R2 by R1 R2. From this we can write R equivalent as R1 R2 by R1 plus R2. Generally we are going to use this formula because we are going to calculate the equivalent resistance for two resistors at a time when we are calculating the equivalent resistance. So in that particular case, the R equivalent can be calculated, that is R equivalent is equals to R1 R2 by R1 plus R2. This is the equivalent resistance calculation when the resistors are connected in parallel. When the resistors are connected in parallel. Now we'll go with the current division from the Kirchhoff's current law. From the Kirchhoff's current law, we are going to get the current division rule, because current is going to be divided in this. Here we are going to consider two resistors connected in parallel, that is R1 R2, and here this is the voltage Vs, I1 I2, and this is the source current Is, where here I1 is equals to, in parallel connected elements the voltage is same for both the elements, or if n number of elements are connected, for across all the elements the voltage is same. So I1 is equals to Vs by R1 and I2 is equals to Vs by R2. So I2 is equals to Vs by R2. Now let us write, because Is current is divided into two, I1 and I2. We have to write in the current division rule, we have to write I1 and I2 values in terms of Is. So for that, let us take the equivalent resistance, that is R equivalent Vs Is, that is Vs is equals to Is into R equivalent. Vs is equals to Is into R equivalent. From this, Is into, when two resistors are connected in parallel, the formula we got as R equivalent as R1 R2 by R1 plus R2. Let us substitute Vs value into this equation. Let us consider this as equation number 1. This is equation number 2. Substitute equation 2 in equation 1. Substitute equation 2 in equation 1. So from this we will get I1 is equals to, in place of Vs we have to write Is into R1 R2 by R1 plus R2. Is into R1 R2 by R1 plus R2 whole divided by R1. This is R1 will get cancelled, will get Is into R2 by R1 plus R2. This is I1. And I2 is equals to Is into R1 R2 by R1 plus R2 whole divided by R2. R2 will get cancelled. Is into R1 by R1 plus R2. This is the I2. Here, by seeing these equations, these equations, we can say that current flowing through any parallel element is equals to whatever the current which is entering is multiplied with opposite resistance divided by sum of two resistors. And this is applicable for only when two resistors are connected in parallel, not for n number of resistors. This is applicable for only when two resistors are connected in parallel. That is, whatever the current entering multiplied with opposite resistance which is connected divided by sum of resistances. This is current division rule. These are the two Kirchhoff's laws, and from the Kirchhoff's laws we have also taken equivalent resistance, voltage division and current division. Now we'll go with some equivalent resistance problems. Here some resistors are connected in different fashion. We have to see whether they are in series or parallel. How we have to say whether they are in series or parallel is, if the current flowing through the elements is same, then we can say those two elements are connected in series. If the current is different, then we have to check for the parallel combinations. The parallel combinations will be, the current entering current should be equals to the leaving currents of those particular two elements. Then we can say that they are connected in parallel. So here, if you see this circuit, if you give, let us consider the current is entering from the node A. These are the two terminals which are given, A and B terminals. Between these two terminals only we have to calculate the equivalent resistance. So here let us give some current Is, and this current is dividing into two, that is I1, I2, and these two currents are divided, and this I1 current is flowing in the 4 kilo ohms and 4 kilo ohms. Okay, let us consider this is R1, R2. In this R1, R2, the same current, I1 current is flowing. So we can say that R1 and R2 are in series. Clear for everyone? I1 is the current which is flowing through R1, R2. So we can say that R1, R2 are in series. So R1 and R2 are in series. So R equivalent 1, let us consider the equivalent resistance between these two resistors. Let us consider it as R equivalent 1. R equivalent 1. R equivalent 1 is equals to, when the resistors are connected in series, the formula is R1 plus R2, that is 4 kilo ohms plus 4 kilo, that is totally 8 kilo ohms. And in the same way, I2 current is also flowing in R3 and R4. There is no other path for the current I2. So we can also say that R3 and R4 are in series. R3 and R4 are in series. So R equivalent 2 is equals to R2 plus R3, that is equals to 4 kilo plus 4 kilo, that is 8 kilo ohms. Now we have to replace the circuit with these equivalent resistance. So here the circuit will be this is A, this is B, this is 8 kilo ohms, this is 8 kilo ohms. From this, if you see, the current entering is dividing into 2 and the same current is leaving. So we can say that 8 kilo ohms and 8 kilo ohms are in parallel, R equivalent 1 and R equivalent 2 are in parallel. So final R equivalent or RAB is equals to, when the resistors are connected in parallel, the formula is R1 R2 by R1 plus R2. R equivalent 1 into R equivalent 2 by R equivalent 1 plus R equivalent 2, which is equals to 8 into 8 by 8 plus 8. I am not writing kilo here, so finally I will write. So 64 by 16, 4 kilo ohms. This is the way we are going to calculate the equivalent resistance between the terminals. Now we'll go with, for the same circuit, if the terminals are changed, how we are going to calculate the equivalent resistance. Now the terminals are changed, C and B. When these terminals are changed, so we have to check that current is flowing from any one terminal. So here the current is dividing, that is I1, I2. I2 current is flowing only in 4 kilo ohms and I1 is current is flowing in all these 4 kilo ohm resistors. So from this we can say that this is, let us consider RA, RB, RC. RA, RB, RC are connected in series. When these are connected in series, R equivalent 1 is equals to 4 kilo plus 4 kilo plus 4 kilo, which is equals to 12 kilo ohms. Now let us replace the circuit with this 12 kilo ohms. 12 kilo ohms, 4 kilo ohms, C and B terminals. So now with this, by giving the current direction, we can say that this 12 ohms and 12 kilo ohms and 4 kilo ohms are in parallel. So RCB is equals to 4 kilo ohms into 12 kilo ohms by 4 kilo plus 12 kilo. That is equals to 12 fours of 48 kilo by 16 kilo, which is equals to 3 kilo ohms. So this is one of the way to calculate the equivalent resistance between the terminals. So when the for the same circuit, when the terminals are changed, the equivalent resistance value is going to change, because the resistors are going to be connected, or how they are connected, whether they are connected in parallel or series, is going to change based on the terminals which are given in the circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.